Okay, it's about 1:30, so I'm going to go ahead and get started here. I'm going to start by sharing my screen. Okay. All right. So before I jump into this session, I'm going to start by just explaining briefly what we're going to talk about. And then if some of you decide you want to go to the ML, that's fine. Yeah, go ahead. It's not on. How about now? Is that better? Okay. Okay. Yeah, so I'm going to start by just talking a little bit about what this session is. So this session is called Deep Learning, and that is what we are going to do some deep learning in this session. But it's really, to a large extent, it's a technical introduction to PyTorch, the library, which is one of the 2 or 3 big libraries that people use most often. So you've probably heard of PyTorch. You may have heard of TensorFlow as well, maybe JAX or QPy. I primarily use PyTorch. I've used TensorFlow a little bit, and there's nothing wrong with it. My understanding from talking to people who use it a lot more is that TensorFlow is more commonly used in industry, and PyTorch is more commonly used in academia, and that fits with my experience. But regardless, what I kind of wanted to say up front is that I'm going to assume that you already have a pretty good grasp on the basics of machine learning. So things like cross-validation, I'm assuming that you already know about this. And I'm not going to spend any time talking about it. We will do cross-validation when we train our network, but it's going to be, I'm just going to kind of gloss over the details of that. And we're mostly going to focus on like, okay, here's how we get our hands dirty with PyTorch. If you think you should be in the machine learning course, I will not be offended if you leave now. Go ahead. All right. Any questions about the topic before I start? Okay. All right, so we're going to do this in the Jupyter Hub. PyTorch is already installed on the Jupyter Hub. And before I get started, I just want to point out, if you go to the curriculum directory, can you all see this okay? Big enough? Okay. If you go to the curriculum directory and go to Benson Deep Learning, there is a file here that contains the whole lesson we're going to do. I'm not going to use this. This is more for your reference after the fact. If you want to keep it open while we do this, it's just kind of a preview of what I'm about to type. So I don't know if it will make me look less impressive or something, but you're welcome to do that. I'm just going to be live coding it though. So I'm going to go ahead and start a new Python notebook here, just a blank one. And I would encourage you to do the same thing and just kind of follow along with me. This is going to be a live coding demo where we just kind of code together. If you get errors or anything, we're a small enough group, just shout it out or raise your hand or whatever and let me know. People on Zoom, it's really hard for me to monitor the Slack and I don't have an assistant to do it today. So please shout out, or I think if you raise your hand in the Slack reaction, I can see it. But if I don't seem to be responding, we can hear you in the room, so just let me know. Okay, if people ask questions on Slack, let me know. Thanks. Okay. So let's start with the general, what is PyTorch? Well, we've used NumPy before. I'm going to assume you've all used at least a little bit of NumPy. And NumPy is this great library for tracking arrays and for doing operations on arrays. And it's not just array operations. There's Fourier transform libraries in NumPy. And there's libraries for doing various kinds of matrix decomposition and linear algebra stuff and all kinds of things in NumPy that are kind of, it's really a generic numerical library. PyTorch has a lot of those same utilities in them. It's just written in a different framework that lets it track certain data that are very useful for optimization specifically. So before we get too far into this, I'm going to give you the world's fastest introduction to the general idea of optimization. This may be a review for some of you, and I'm going to do this really inadvisable thing, which is do this introduction by drawing it on a trackpad for you all. So we'll see how this goes. Okay, the kind of classic optimization problem. And just to back up just a little bit, when we train neural networks, we're performing an optimization problem. And what we're trying to do is optimize the parameters of the neural network to best predict the data set we have. That's basically an optimization problem where we've got a bunch of parameters, and by fiddling with them, we can make the model perform better or worse. And if we fiddle with them and it gets a little better, that's good. And we keep fiddling with them in that general way until it gets good enough that we're happy with it. Now, the notion of fiddling with the parameters, what does that mean? Well, we could just randomly choose a bunch of parameters and see how it does, and then do the same thing again, and do it again, and do it again, and keep the best model. That's one way to do optimization. It's just not a very efficient way. It'll probably take millions and millions of draws of parameters before we get even a reasonable model. However, there are some very useful techniques for optimization. So let's take a very simple optimization problem. This is X and Y. And we have, we're going to optimize, the idea is that there's some function we have, f of x. Okay, writing text is not going to be a thing I do with this. We have some function f of x. We don't necessarily know what the form of that function is. It's coming from some other library, or it's something that's very difficult to calculate. But we can graph it, and let's suppose we graph it, and it looks kind of like this. Okay, something like x squared shifted a little bit. That's approximately what our f of x looks like. So if we want to find the minimum value of this function, we can guess an x and see what it is, and then we can guess another x and see what it is, and we can do that over and over again until we get the smallest x. But again, that's a very inefficient way to do it. Instead, we can guess an x to start, like let's guess this x right here. And we can calculate f of x at that position, and that tells us here's the y value. Okay, now we can calculate the derivative at x. And we can definitely calculate a derivative at x because we can just adjust x by a little tiny bit and take the difference and do a finite differences derivative. So we can calculate the derivative, which is going to be some line with a slope right there. And in this case, the derivative is going to point this way, essentially. But we can take a step in the opposite direction of the derivative. So we can say something like, look, wherever this derivative slope intersects with 0, we're going to move our x to there. And then we're going to start over and say, this is our new guess right here. And now we go down and we find that the f of x at that x is quite a bit closer to the 0. This is the basic idea behind Newton's method of optimization. And I picked, the way I drew this was maybe not super useful, but like if we start out here and we get something like a derivative like this, we may end up with an intersect here, and then we use this x and we start over, and now we get the derivative here, and there's our new intersect, and we can get a new x and f of x, and we can just keep doing this and keep following the derivative until we get to a point that we kind of iteratively approach where the derivative is flat. And when the derivative is flat or the derivative is 0, we've reached some kind of minimum or maximum. Okay, this is a very kind of simple example of an optimization problem. I just wanted to kind of present this context. Almost all optimization that we do, almost all numerical optimization, follows an algorithm basically like this. Now, when we're doing optimization in the real world, it's usually not just f of x, it's f of x1, x2, x3, x4, a bunch of different variables. But the fundamental thing we're doing in the optimization problem is picking a random point, calculating a gradient, following that gradient towards the 0, and it will iteratively bring us closer and closer. We don't need to understand the math behind this process for this lecture. I just wanted this to kind of be fresh in everyone's minds. Any questions about this? Okay. So keeping in mind that this is essentially how we do optimization. A lot of what PyTorch handles for us is the machinery that's necessary to solve these kinds of problems. How do we calculate the gradient of a very complicated function we're running? How do we calculate that derivative? And then how do we take a step along that derivative towards a smaller value in the function? Okay, I'm going to clear all that and hopefully not draw anymore. All right, so we're going to start by the basic way we're going to organize the rest of this lecture is we're going to start by just playing around a little bit with PyTorch, just enough to see kind of what it is. We're going to set up an example optimization problem, kind of like the one I just showed you, and we're going to solve it. And then we're going to build a neural network. And if we have time at the end, we can try to build a convolutional neural network specifically, although we may not have time for that. Okay, so just to get started with PyTorch, let's go ahead and import Torch. I'm going to make this just a little bigger. And I'm going to go ahead and collapse the side panel so it's easier to see. Okay, we can import Torch. Hopefully this does not cause any errors. If it does, we're in trouble. All right. Now, you might be, I'm also going to go ahead and import NumPy as NP just so we can compare them. And because we're probably going to want to use this eventually, I'm going to import matplotlib.pyplot as plot. Okay, so you've probably all seen the numpy.zeros function, where, for example, if we want a matrix of 2x3 matrix of zeros, we can say, hey, NumPy, give me a 2x3 array of zeros, and it does that. Torch has a very similar function called zeros, where you can ask for a 2x3 array of zeros, and it gives you back not an array, but a tensor. Tensors are just mathematical names for arrays. There's nothing really different about them, but PyTorch calls its data types tensors, whereas NumPy calls them arrays. Now, notice that these look pretty much identical except NumPy versus Torch, and that's by design. PyTorch, for the most part, its interface is almost identical to NumPy in most places. And I say almost identical. It's identical for a lot of operations, the common operations that you use. There's places where they differ, but if you know how to use NumPy, then you can probably use most of the functions in PyTorch without much trouble. Okay, so we can make this, let's say u is equal to torch dot zeros. And we can do pretty basic kind of operations on these tensors just like we would on a NumPy array. So here I'm going to set all of the elements in the first column to be 1. And then I'm going to say something like u equals u minus a half times 3. And I'm just going to print u. And we can see that that works. This is a perfect, just like this was a NumPy array, this whole set of math works, and that's because PyTorch tensors are designed to operate just like NumPy arrays for the most part. Now, despite the fact that they seem to have the same interface and they seem to be the same data type and they store the same kind of data, NumPy and PyTorch don't actually always work together very well. So just be warned that if, for example, you made an array U and you wanted, or let's say you make a NumPy array of zeros called A, and then you want to take the mean using Torch, that's going to give you an error. The input must be a tensor, not a NumPy array. So PyTorch only wants to operate on PyTorch objects. And generally will not operate on NumPy objects. Every once in a while, there's a function that'll let a NumPy object through, but for the most part, you can't use NumPy objects with PyTorch functions. The flip side of that is not necessarily true. If I try to have NumPy calculate the mean of a tensor, in this case, it's going to give me an error because well, in this case, it's not going to work, basically because whether a NumPy function works with a PyTorch tensor is going to depend a lot on both the tensor and the NumPy function. So certain tensors, which we'll see in a little bit, are specifically designed to track the calculations that they're involved in so that we can calculate derivatives more easily. And if you're tracking derivatives or gradients, then in general, it won't let you use it with NumPy. Occasionally, NumPy functions will work with PyTorch tensors. I don't have a hard and fast rule for when they work with PyTorch tensors, but frequently they will work with them. And part of that's because NumPy is designed to work with any kind of input. Like you can give NumPy a list and it will treat it like an array. So in general, if NumPy can get away with treating a PyTorch tensor like an array, it will. That obviously doesn't always work though. Okay. Fortunately, it's pretty easy to convert between them. If you've got an array like this NumPy array A, we can always just convert it into a tensor by calling torch.tensor. And that will make a tensor that's equivalent to that numpy. If we have a PyTorch tensor like this tensor U we made, we can call u.detach.numpy. And that will turn it into an equivalent numpy array. Now, you might think that you should be able to just call u.numpy and are wondering why we have to have this weird detach function in the middle. The purpose of this detach function is to basically say, look, PyTorch is as I'm programming PyTorch or running this program, PyTorch is busy tracking all these calculations I'm doing in case I need to calculate a gradient or a derivative. And so this tensor U is caught up in those calculations. And if we take a NumPy copy of U, what NumPy actually returns is the same data as is in that PyTorch tensor, just as an array. So if we took that undetached array and we changed it, we would screw up all that calculations that PyTorch was tracking in the background. So by calling detach, we basically say, PyTorch, take U and extract it from all those calculations. Give me a copy that's not connected to those calculations anymore. And then give me a NumPy array of that tensor, and that's safe to work. Okay, any questions so far? All right. Okay, so these are just some very basic kind of ideas. In general, if you can run a NumPy function like numpy.exp, for example, there's a PyTorch equivalent. So you can do pytorch.exp, we'll just pass it U, and it works pretty much exactly like the NumPy version would work. As a general rule, this will usually work. For the most part, they have the same interface and work the same. You just have to give them tensors. Okay, so let's go ahead and talk a little about an optimization problem or work on an optimization problem here. So for this is a completely made up problem, but I'm just going to start by defining, by defining a curve function. So we're going to define a function curve. This is a parametric curve that takes an argument t. Everyone know what a parametric curve is? Anyone want me to explain that? Okay. Yes? Okay. So a parametric curve is where you have some variable t and you have a function f of t, which equals x of t, y of t. And so, for example, you might say x of t is equal to cosine of t and y of t is equal to sine of t. And when you plot x and y against each other, that makes a circle. That's a parametric function of t, or a curve of t. So we're going to define a parametric curve in exactly that way. And in fact, it's not going to be all that different than a circle, just a little bit. We're going to say x equals torch dot sine of t minus a half. We're going to say y equals torch dot cosine of t times 2 plus torch dot cosine of 2 times t plus 0.75. Return x, y. So there's our curve function, and if we, for example, say curve of a half, it gives us an error. It says we have to give it a tensor. And that's because, like I said earlier, PyTorch really only wants to work with tensors. So even if we just want to pass a number to a function like torch.sine, we need to make that into a tensor, like this. And then we get back to individual tensor numbers. Does everyone know that you can have a single number in a NumPy array? Yeah, so you can, a NumPy array, like you can have, for example, an array of 10, and that's just a single number. There's not a list there, it's just a number. PyTorch tensors can do the exact same thing, and it kind of makes sense because in math, at least, zero-dimensional tensors are just numbers. Okay. So that's what we're doing here. We make a tensor of the number half, and then we can pass it through and get these numbers out. Okay. So let's go ahead and maybe make a plot of this. I'm going to say t equals torch dot linspace. Linspace takes two numbers and the number of points between them that you want, and it gives you evenly spaced values between those two numbers. So I'm going to say 0 to numpy.pi times 2. So from 0 to 2 pi, give me 100 points. I then say xy equals curve of those points. And just like how NumPy will work for, you can call sine of t for a single value or a list of values, PyTorch will do the same thing. So this will give us back a list of x's and a list of y's. And then we can say plot plt for pyplot.plot x comma y, and we're going to tell it to color that as a black line. Now, we saw that NumPy didn't like to take PyTorch tensors as inputs, but pyplot doesn't really care what kind of inputs you give it. It just cares that it can iterate over them. So this will work just fine. At least I worked last time I tried it. And I'm just going to add some axes real quick. So if we want to go from -3 to 3 at y equals 0, and I'll have a line width of a half. And I'm going to put the same thing, but for the varying the y. Okay. Whoops, I did not write numpy.py, I wrote np.np. That should have been np.py, so 0 to 2 pi, and points in between. Okay, so this curve looks a little bit like the Star Trek communicator symbol, I guess, but this is just a random curve. And as an example of an optimization problem, let's suppose we just want to find the point on this curve that is closest to the origin. I think that it's not obvious just from looking at this where that point is. I mean, it's somewhere in this area. I'm pretty sure that it's over here. It's not over here somewhere, but it's probably not here. It's probably over here somewhere. And finding that exact point is kind of tricky. So we can do it by optimization though. So if we want to try to optimize to find optimize to find that point, what we're really doing is picking a point on this curve, picking a t, and then figuring out how far it is from the origin, and then finding the gradient of that and trying to move closer and closer to where that distance from the origin gets smaller and smaller. So if you think of it in terms of our random optimization example earlier, where we're not actually doing an iterative optimization, we're just guessing and trying over and over again. We just guess a point along the curve and then see how close it was, and after a bunch of guesses, we take the shortest one. But if we want to do that, even if we want to do just that simple version of an optimization, we need to start by defining the actual function whose value we're minimizing. So we're going to call this the loss function. We're going to define it as loss. And for whatever reason, I used to call this like an error function, but for whatever reason in machine learning, people tend to call it a loss function. So we're going to have a loss of t. The first thing we're going to do is we're going to calculate the actual curve position for t. We'll get the x and y. And then we're going to calculate the distance. I'll say distance from origin is torch dot square root of x minus 0 squared plus y minus 0 squared, right? And then we can just return that distance from origin. Now, the important thing about this loss function is that when the value returned by the loss function is smaller, we're closer to the value we're looking for. We're closer to the thing we're optimizing. So far, does this make sense to everyone, what we're doing here? Any questions? Mm-hmm.
Do you like a neuroscience with space and how exactly like this?
Yeah, so this is obviously a very contrived example. Now, what I've used this for is if, for example, I have a map on cortex, on the cortical surface, and I've got a bunch of different vertices that are all next to each other, like adjacent to each other. And I have some model for what this map should look like. In my case, I'm usually looking at the visual cortex and like a retinotopic map in V1, for example. And I want to have that model has some kind of smoothness that's enforced over the cortical surface. I would set up a loss function that said something like, how smooth are these data? I can calculate that by looking at pairs of vertices on the surface and seeing how different they are. And the more different they are, the less smooth it is. And then I can minimize the sum of differences between those vertices. So that's a much more complicated example but it's the exact same kind of setup we'd use here. We'd have a loss function that just calculated that sum and then would try to minimize it. So I totally acknowledge this is a very contrived example that has very little to do with neuroscience. I'm just using it to kind of introduce the general way we run an optimization problem in PyTorch. Yeah. Any other questions? Okay. Okay, so we have set up a loss function here. If I do something simple like run the loss of 1.5, we can just check it. Of course, that's going to give me an error because I have to give it a tensor. So if I ask for the loss of the tensor of 1.5, we get a loss. And that's a single number. Okay, so what if so obviously for the optimization kind of problem, we need to calculate a gradient so that we know how to step kind of along the gradient. And here's where PyTorch really does something that I think is kind of magical. It's not magical, it's math, but it's like the fact that there's a implementation of this that works and is very efficient is what's magical. So I can say something like t equals torch.tensor of 2.1, and I'm going to say requires grad equals true. That just means that for this tensor, I want to be able to ask questions about the gradient of what I'm calculating. That's what that means. And then I'm going to say the distance is equal to loss of t. So we calculate our loss function here. And then I'm going to run dist.backward. Now, this method backward is for a backward gradient calculation, propagation calculation. We don't need to talk too much about how this works, but the basic idea is that you can, by kind of looking back up through a series of computations that have been performed, you can always arrive at the correct derivative for something. That's also just math. In intro calculus, you learn that you can find the derivative of anything, but you can't necessarily find the integral of everything. And this uses that basic principle. We can always computationally find the derivative. And this backward function is what does that. And once we've run dist.backwards, we can ask for the gradient, t's gradient, and it will tell us that the gradient at t is negative 2.35. And that tells us that if we make t smaller, the value of the loss is going to get bigger. And if we make t bigger, the value of the loss is going to get smaller. Okay, this is a good point to pause for questions because there's a lot of weird math in there that I just kind of glossed over. Anyone have any questions about that? If nothing else, the thing to understand here is that we calculated a value in terms of t using some function. And then we asked PyTorch, hey, what's the gradient of this function in terms of t? And it told us. And even if t, so for example, if this loss function took like 100,000 parameters, it would give us back 100,000 dimensional vector of the entire gradient in terms of all those parameters. So this is actually a very powerful calculation that PyTorch performs for us. Okay, so we can calculate a derivative. So let's go ahead and actually do an optimization in PyTorch as we would. And this, what I'm going to set up here is basically the exact same way we'll do it for the neural network in a minute here. But we're going to start by saying t equals torch.tensor. T equals torch.tensor 2.1. That's our starting guess. We're going to start with 2.1. We're going to say this requires the gradient because we're going to need to calculate the gradient as we go. And then we create what's called an optimizer. So the optimizer manages the taking of steps over and over again until we get to a minimum value. And there's a bunch of different optimizers built into PyTorch. If you just Google PyTorch optimizers, there's pages and pages of different optimizers and different strategies for trying to optimize. For the most part, we won't worry about these. We're going to just use the most common optimizer. We're going to create torch.optim.sgd. SGD stands for stochastic gradient descent, which is just literally the example we talked through earlier, where you just kind of follow the gradient towards the zero or towards the minimum. We have to tell it what the parameters we're optimizing over are. So we tell it that we're optimizing over t. And we have to give it a learning rate. which I'm going to set as 0.05. The learning rate is basically, once you've calculated the gradient, you have to decide how far along that gradient you're going to take a step. You can follow it really, really far and you'll end up farther away from the minimum than you started. Or you can follow just a little tiny step and you'll get closer to the minimum, but it's going to take a long time for you to get there. For the most part, the learning rate is going to depend on the problem you're solving. Like the learning rate you need to use will depend on what kind of problem you're solving. 0.05 is a good initial guess, but you kind of often have to just kind of play around with the learning rate until you get a value that works well. Unfortunately, a lot of these kinds of optimization problems are engineering problems. So I can't necessarily give you a formula for how you would find this value. I can just tell you that you have to experiment with it until you get one that works pretty well. Once you find one that works pretty well, you should be able to tweak it without changing it very much, and it should give you the same answer. And if it doesn't, then you have a problem. But as long as you kind of find a learning rate where you get the same answer as you tweak it a little bit, you've probably found a good one. Okay, so we create an optimizer, and now we're just going to go in a loop. We're going to say for step number in range 20. I'm just saying we're going to take 20 steps of minimization and see how far we get. And obviously, if you take more, you will get closer, or maybe not. It depends on depends how close you are when you start. We're going to start by saying optimizer.zeroGrad. This is a step that we have to run that basically says, this just tells the optimizer we're starting a new iteration of the training. We need to clear all the gradient calculations you've been keeping track of and start over. We then go ahead and calculate the loss like we did before. We say dis.backward like we did before. And then we tell the optimizer to take a step. And that's really it. That's all the code you need for optimizing this. Now I'm going to add one more line here. I'm going to put a print statement so we can watch it. So I'm going to say step number. Say t equals float of t, and we're going to say loss equals that. Okay. And then finally, at the very end, we're going to say print done. We'll print the final value we found and the loss. Okay. So when we run that, we see it goes through a bunch of steps pretty quickly. Step 0, we have a loss of 0.833. After the first step, we have a loss of 0.830. You can see this is slowly going down. And eventually it gets down to about 0.448. Now, I don't know that this is, what you can see is that it's still getting smaller at the end. So that means we probably didn't take enough steps. It's still getting smaller fairly quickly even, but nonetheless, let's just look at the point we found here. So this is the final t value we found. So I'm going to copy that. And I'm actually, just to make this a little faster, I'm going to scroll back up to where we plotted the function earlier. And I'm just going to say found t is this value. And I'm going to find x and y of that value. And then I'm just going to plot a red dot. Oh. That didn't seem right. Yeah, that won't be the difference. That's the kind of dot that it's using. That'll be a smaller dot. Okay, I think I need to detach these. Oh, of course. I used t here instead of found t. Thank you. That should have been an obvious one. Okay, try that again. There we go. So there's the point it found. And I at least would agree that that's reasonably close to the right answer. I'm pretty sure it's got to be over here somewhere. So this just kind of verifies that it worked more or less. So the point here, now again, this is a very contrived example. The point here was just to show you that there's a little bit of like arcanistry here. Like you need to know a few function calls and stuff and how to set this up, but it's really not that complicated. The amount of code you need to run a real PyTorch optimization problem is only about 10 or 20 lines, as long as you've got a reasonably defined function. And a lot of the complexity that you would normally have to manage when you're doing optimization, like calculating a derivative, that's all handled by PyTorch. Any questions so far? Yeah.
Tell us where is the magic here, like, you know, for instance, the link between T
Uh-huh.
and the distance and the loss is because PyTorch is doing that import in the function.
So
is this
yeah.
this from origin for torch per square, like, you know, like that is where it's linking that object to
Correct.
that object here.
So when you calculate something with PyTorch, like when you call like sine of x, PyTorch will look at x and say, are you tracking the gradient for x? And if you are, then it will give you back a value, a torch tensor that has the answer, but attached to that tensor is information about the sine calculation you just did. So that then when you say, okay, take that sine value and give me the gradient, it can look at that and say, oh, the gradient of sine is cosine. So we just substitute cosine x and that's your gradient. That's where the magic is that behind the scenes, no matter how complicated this loss function is, as long as you're using PyTorch functions to calculate it, you'll always be able to get a derivative out. Yeah. Okay. So when I first discovered all of this in PyTorch, I was so enthused because I had been writing code that calculated my own gradients for a long time. And obviously you've all never done that probably, but if you had, I promise you'd be as enthused as I was. Anyway, let's actually talk about neural networks now. So for the rest of this, well, we'll see. We may have time to do a convolutional neural network, but starting here, we're going to work on an actual image classification problem. So has anyone heard of the MNIST dataset? Oh, good. Yeah. So MNIST, actually, there's multiple MNIST datasets, but in particular, there's a dataset of numerals of like people have written out like the number 4, and it's been labeled as a number 4. So it's sort of like pictures of handwriting, and it's a labeled dataset of images of handwriting with the actual numeral that was written. So that's a great data set for a neural network, because what we're going to do is we're going to train the neural network to look at that image and tell us what digit is presented there. So the first thing we need to do is load in the data set. So for that, we can actually just use the torch.load function. I've already put the data set on the shared drive. So we're going to say, whoops. We're going to start by saying training labels and training images equals torch.load. And then we just need to give it the file name, which is /home/Jovian/shared /Benson-deep learning /mnist_training.pt. PT is a common PyTorch file extension. And you can use the torch.save function to save out arbitrary torch tensors and such. So this is going to go load this file and give us back a set of training labels and a set of training images, which we'll look at in just a second. We're also going to pass an optional argument weights only equals true. That basically prevents it from giving us a warning about security issues. And then we're also going to do the same thing for our test data set. Test labels, test images equals torch.load. And I'm going to actually copy paste these 2 lines because they're almost the same. It's just that instead of mnist train, it should be mnist test. Okay, now that should take just a second to load in. And let's just take a quick look at what actually got loaded. So training images is a tensor. Whoops, I spelled something wrong. Training images is a tensor that's 60,000 by 28 by 28. That's because it's 60,000 very small images. So let's just plot one of those. If I just take training images and I plot like the 10th or the 11th, I guess, training image, we can see that that is probably a 3. Or different one. I have no idea what that is. Maybe it's a 7 or a 5. So you can see this is actually going to be a hard problem. It's not going to be that easy. But regardless, we have just a whole bunch of numerals that people have written. And this is clearly a 9. So if we look at training labels for 110, once again, I misspelled it. We have a 9, matching this 9. Oops. So basically we have a tensor of images and a tensor of labels. And both the training labels and training images and the test labels and test images are the same kind of data structure. This makes sense to everyone? Any questions? Okay, so that's our data set. Basically, what we want to do is we want to train this neural network that we're going to build to look at those images and tell us the label. So before we build the neural network, we need to set up a data set in the format that Torch likes. So Torch, PyTorch has a data set class, and we're going to use it. So basically, we're going to make our own class. MNIST data set. And we're going to have it inherit from torch.utils.data.dataset. I know we don't really talk about object orientation and inheritance in classes in this course very much. If this is all new to you, don't worry too much about this. This is basically just a way that we can kind of tell PyTorch how our data fits into its interface. And we do that by saying we're making our own custom dataset class that's based on PyTorch's dataset class. And we're going to define an initialization function. That's underscore underscore init underscore underscore. And it takes 3 arguments. The first is itself, the class instance, and then images and labels. And this is very simple. We're just going to say self.images equals images. We're going to convert that to a float like that. Self.labels equals labels. And then we need one more function, get item, self index. And this get item method, this is the method that actually gets called when you do something like RF10. When you make a call like this on a NumPy array, it goes and looks up in the R object. It finds the get item method and calls that with the value 10 for index and self for R. So that's all that this is. And PyTorch, all that PyTorch wants you to do to have a properly functioning data set is return whatever your training data and your label are as a tuple for that index. So what this means is we're just going to say return self.images index, self.labels index. That's the entire dataset class. Oh no, I lied. There's one more function. We have to define a length. And that's just going to be the same as the length of the labels. Okay, that's the entire dataset class. And then we can go ahead and make, if I can spell it right, training data equals MNIST dataset of training images, training labels, and test data is MNIST dataset of test images, test labels. Okay. I'll leave that up long enough that you can see it. But once we've made this, we can ask for something like, okay, what is the 110th entry in our data set? And we get back a tuple of the image followed by the label. Does that more or less make sense? Any questions on this? Okay. Say again? Why do we need the class? So if we didn't make this class and we just tried to use the torch.utils.dataset class, it doesn't know about our particular images and our labels. It doesn't know how to handle them. And so in fact, this dataset class is what's called an abstract class. It's not entirely finished. It doesn't have all of its methods. And it needs these two methods specifically. So we kind of had to tell it the rest of the logic, and it's very simple. It's just needed to know how to do that. Yeah. Yeah, good question. Any others? Okay. Can I scroll past this? All right. Okay, so we've got data sets set up now. We are actually almost ready to do the training, just about. We still need to make a neural network. Okay, we'll skip this for now. Okay, we did look at the images already. Okay, so let's go ahead and make, what we need to do now is we need to build a neural network. And we're again going to make a class that's going to inherit from PyTorch's sort of model class. Now, one of the main things PyTorch offers is a whole bunch of tools for building models. And these models may be just simple mathematical, like algebraic models, or they may be neural network models. And PyTorch has the same basic structure for building all of those. It's real simple. We're going to say class, and I'm going to call this neural network. Whatever you wanted to call your class. And we're going to inherit from torch.neuralNetwork.module. Now, the module class is another abstract class, and it needs us to, it's got a whole bunch of utilities kind of built in, but it needs us to tell it how we actually calculate the model values. Because it's a generic model class, it doesn't calculate any particular model. So to do that, we have to define a function called forward. That takes as arguments. Now in Python, in classes, the first argument for a method of a class is always the object itself, the self object. And then X is just the input to our model. So we have a model that takes some input and calculates some value, and X is our input. And this forward function just needs to return the value that the model calculates. So it's a pretty straightforward kind of interface for this class. And what we need to do is define our neural network and have this function calculate the result. So we're going to also have an init function. It's not going to take any arguments. It's just going to be a plain initialization function. And we're going to go ahead and first of all, call the modules initialization function. So we say super neural network self.init. Okay. Then we're going to go ahead and create what's called a flattening operator. This is torch.neuralNetwork.flatten. The flattening operator, the idea is that when you give it like an image, it's just going to turn it into a vector. That's all it's going to do. And we'll see how we use this in just a second. And then we're going to create what's called a linear stack. And we're going to use torch.neuralNetwork.sequential. This sequential just means that we're going to give it a sequence of operators, and we want it to apply them one after the other, where we give it input, and the output of the first operator goes into the input of the next operator, and the output of it goes into the input of the next one, etc. So it's sort of like a list of filters. The first thing we're going to give it is torch.neuralNetwork.linear. We're going to give it 28 by 28 and 512. So what does this mean? 28 by 28 is the size of the input images we have. So we're training it to recognize 28 by 28 images. And what we're going to do is when this model gets one of those images, it's just going to flatten it into a vector of 28 by 28 values. And then neural network.linear is just a very simple all-to-all neural network where it takes each of the 28 input values and connects them with a weight to 512 output values. So in neural networks, a lot of what's going on is that you've got inputs and outputs, and you've got some weights in between them. And what we're training is the weights. So you can think of kind of every output value as a weighted sum of the input values. And we're training what the weights on that sum is. So inside of this linear operator are weight parameters that turn these 28 by 28 into 512. And when we optimize for this neural network, we are optimizing over those weight parameters to find the ones that give us the best answers. After this, we're going to add a torch.neuralnetwork.ReLU. ReLU stands for rectified linear units. It is a very common operator in neural networks. All that it means is that it takes all the values that are less than 0 and sets them to 0. That's really all it does. And this tends to be really important in neural networks. And for some intuition as to why, you can think of this as almost like a test or an if statement. It's looking at the outputs and saying anything less than 0, we're going to cut off. So that's almost like the neural network saying, okay, we've run one calculation, we're going to discard some values that are below some threshold. Now, if any of you have worked with neural networks before, you probably realize this, but the reality of neural networks is that it's really hard to understand what's going on inside of them. And in fact, there's a whole lot of literature about neural networks that talks about what goes on inside of neural networks that often uses intuition rather than like math to try to describe what it is. And oftentimes these kind of explanations are very hand-wavy and not really clear as to what they do. And this is kind of one of these. It happens to work really well when you add rectified linear units in the middle of your neural networks. It makes them better. I don't have a really strong mathematical explanation of why, but the intuition I can give you is that by creating some kind of like decision point in the middle, you give the neural network a little bit of scaffolding to kind of make a decision in its weights that allows it to produce a better answer. Yes, yeah, it's a sparsity thing.
What if you had a 1048
up here?
Like, because more output than input in that case.
Yeah. So so a lot of neural networks will like this. Essentially, what we're starting with this image, and we're creating kind of like an encoding where we have this weighted sum, and a lot of neural networks create like a whole bunch of space in the middle where you've got more internal parameters than you have like inputs. In theory, you shouldn't get any more power out of that, but sometimes it's easier to train those networks, and so that's kind of why people do that. Yeah. Okay, we're going to add just a couple more layers here. Whoops, we're going to add torch.neuralnetwork. I needed to add a parentheses and a comma there. We're going to add another linear that goes from 512 into 10. And then we're going to end with another ReLU. Now, so we have our first bit of the neural network takes 28 by 28 and turns it into 512 internal parameters. And then we do a ReLU, and then we have another bit of the neural network that takes those 512 parameters and adds them up into 10, uses a weighted sum to add them up into 10 parameters. Now, the reason we're doing 10 is because there are 10 digits, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the way, this is another one of these things where I can tell you what works, and I can't necessarily tell you why it works, but it is what works, and so it's how we build neural networks. If you're trying to get a neural network to guess a number, like 1 through 9, getting the neural network to produce a value 9 is hard, but getting a neural network to produce a really high value in the 9th parameter is easy. And so the way that this network is going to work is it's going to take our image as input, and it's going to give us a vector of 10 values out. And if the first value is the highest value of those 10, we're going to assume it's predicting a 0. If the second one is the highest value of the 10, it's predicting a 1, etc. Does that make sense? Okay. Okay, so this produces an output of 10 length vector if we run it. And that's all we need to put in this initialization function. The forward function is actually where we calculate the model, and it's very simple now. We first of all flatten the input image. So we say self.flatten. And then we say logits equals self dot linear stack of X, and we return logits. Anyone heard the term logits before? No. Okay, some of you. You've all heard the term probability. A logit is related to a probability. Probabilities have to be between 0 and 1. And if you take a sigmoid function that is 0 at negative infinity and that is 1 at positive infinity, then you can convert between a real number between positive and negative infinity and a number between 0 and 1. So probabilities are between 0 and 1. Logits are the equivalent number between -1 and infinity. So it's kind of like sort of like the arctan of the probability or something like that. But so I explained that very fast. If anyone wants a graphical explanation, I'm happy to provide it. Yes, no, anyone? Yes, okay. So let's just, I believe Torch has a sigmoid function built in, so let's just use it. Yes, okay. So if I take X equals torch.lin space from -100 to 100, and I just get like 5,000 values, I can say Y equals torch.sigmoid of X, and then I'm going to just plot X and Y. And this is a sigmoid function, right? Now, if I were going between slightly more reasonable values, it looks a little bit more like an S, but regardless, the probability has to be between 0 and 1, but each of these numbers between 0 and 1 uniquely map onto a single real number using this function. So, so we can convert a real number into a probability using the sigmoid, and we can convert back using the inverse of the sigmoid. So logits are just a representation of probabilities that can be any real number. And the reason that's useful is because if you want a neural network to produce a probability as an output, then it's much easier to train it to produce some real number and not try to constrain it within the values of 0, 1. And then we can just convert it into a probability. So sigmoids come up all the time in neural networks and convolutional neural networks for this exact reason. Okay, so we've built a neural network now. Let me go ahead and create one. I'm going to say model equals neural network. Just like that. I'll go ahead and print it too. Oh, what did I do? Did I misspell it? I didn't run this. Okay, I'll run that. And then I'll create a model. And it has this nice way of printing our model. Even though we didn't tell it how to print these in order, it knows how to do that because it's got all this extra machinery to handle models kind of built in the background. Okay. We're almost ready to actually train this neural network. Recall that what we needed earlier was a loss function and an optimizer. So we'll make those now. We're going to say the loss function, and we're going to use a built-in loss function for this. It's torch.neuralnetwork.cross entropy loss. The cross entropy loss is just, it's a function that specifically takes like a 10-valued output, a vector of outputs, and a number, and says how bad of a prediction did you make in terms of where the highest value was. It's exactly the loss function we need for this this problem. And I'm happy to I can go over that a little later if people want to know what is actually in that loss function. It's basically like a log probability. Okay, and then we also need an optimizer. And once again, we're just going to use the basic gradient descent optimizer. And this time, since we have our model we defined up here, we can just tell it to use the parameters in the model. And even though we didn't write this parameters function, PyTorch knows how to figure that out. So we can just ask the model what its parameters are, and it will get all the weights out of those pieces that we put in there and include them in the optimizer. And then we're going to give it a learning rate, and we're going to use 1e-4 here. Honestly, this value, if you pick -5 or -3 or something, it'll work just fine. Again, the learning rate is a little bit of an engineering problem. Okay. Okay, I think we're finally ready to train the model. So first of all, I'm just going to get the size of our training data set. Training labels. We're going to want to run through each example in the training data set, basically, and then we'll be done. We are, I forgot to make a data loader. Okay, so there's one more thing I forgot, which is we made a data set, but typically when you feed examples into a model, you want to give them in like a shuffled order or a randomized order. You don't want to just give it the same examples in the same order. So PyTorch has a tool for that called a data loader, which will just kind of automatically shuffle things. So for that, I'm going to say train data loader equals torch.utils.data loader. And all we need to do is give it our training data, which is the data set we made earlier, and a batch size, which we'll just use 64. And I'll explain that in just a second. I'm going to copy that line and then do the same thing for the test data. Okay, so this batch size parameter that we gave the value 64, it's generally more efficient to train on a bunch of a group of examples at once. And there's like basically, rather than feed the examples one by one into the neural network, you can feed in a group of 64 of them and have it look across those kind of simultaneously. And that just speeds things up a little bit. This would work fine if we used a batch size of one and fed them in one at a time. It would just take longer to train. That's the real difference there. So these data loaders, they shuffle your data so they go into the model in a random order in the training, and they group them up so that it goes a little faster. It handles both of those. Okay. So all right, so now we're ready to actually do the training. I'm going to say, whoops. Okay, I'm going to say for batch number X, Y. Oh, whoops, this is not, I made that a markdown cell by mistake. Okay, for batch number X, Y in enumerate train data loader. Everyone know what enumerate is? Whatever you're iterating over, it gives you a tuple of the index and then the thing you're iterating over. So this is just going to be, this batch number will just be 0, 1, 2, 3, etc. And X and Y will be what the data loader gives us. Now, because this is a data loader and not a data set, these will be batches. So the size of X will be something like 64 by 28 by 28 instead of just 28 by 28. Okay, so we can go ahead and, well, we'll start by running optimizer.zeroGrad. We'll then, which is what we did before, that just tells the optimizer that we're starting a new step in the optimization. We're going to say prediction is equal to model of our input data X. And models are smart enough to be able to work with batches. So without us doing anything, that'll just work. We're then going to say the loss is equal to our loss function of the prediction versus our true label value, which is Y here. We're going to say loss.backward. And then we're going to say optimizer.step. Now, recall that there were like 60,000 training examples, so there's going to be a lot of steps here. So I'm going to say if batch number mod 100 is 0, we're going to print a message. We'll say, we'll go ahead and, well, we'll just print batch number. And we'll say loss, loss. Okay. Okay, that is a whole training kind of regime for this. Let's see if it works. So it seems to be working. You notice that at the very beginning, the loss value is quite high, 18.9. Now, is 18 high? I don't know. It's really only high relative to whatever we optimize. And if you know exactly what your loss function is calculating really well, this number may make sense to you. In our case, it's hard to say what this number is because it's some difference between these log probabilities of these categories. So 18 isn't something that means a lot to me, but it clearly gets a lot smaller right away. And it generally goes down, although it goes up occasionally. So as you can see, there's a little bit of randomness in this whole process because we're getting the images in a random order, and we may get an image that causes the training to do something a little weird. And that may result in the model going up in its loss for a little bit. Ideally, if things are working well, it will generally go down. And we see that it did generally go down. We ended up with a quite a bit lower loss than we started. But is it working? Well, let's just draw some random examples and see how well it works, since we now have a trained model. So I'm going to go ahead and make some plot axes. I'm going to set up 4 subplots. And then I'm just going to flatten these axes. So we have a vector of axes. And I'm just going to say for X, batch, Y batch in test data loaders. Test data loader. Now, we did all this training with the training data sets. This is where cross-validation comes into this lecture. We did all the training with the training data sets. If we want to see how well it does, we shouldn't use the training data set to test it. We should use the test data set, which it's never seen before. And that's what we're going to do. So if I iterate over the test data set, what I want is that every time I run the cell, I want it to randomly choose a different image. So I'm going to use a really simple way to do that. I'm just going to ask, say, if numpy.random.rand is less than 0.9, continue. So this is a really kind of hacky way to do this, but it's basically saying draw a random number between 0 and 1, and 90% of the time, start this loop over and get the next set of items out of the data loader. This way, every time I run this cell, it'll randomly choose a new set of images, and we can look at a few different outputs. That's all. Okay, so we've got that. Now I'm going to say since we got to this point, I'm going to say for x, 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 y in zip, axes, x batch, y batch. So this is going to iterate over our axes, inputs, and labels. I'm going to say x.imshow of our image. And I'm going to get a prediction from the model. Whoops. Now, I've got to add a kind of funny little thing here. Have any of you seen this syntax before in the context of NumPy? Okay, so there's a weird thing about NumPy that you often need. If I have like an array of 1, 2, 3, for example, this is a one-dimensional array, but sometimes I want it to be a column vector. And if I want to treat this as a column vector, I can, you can ask for this, and that'll give you just the same array back. But if you put a none in the arguments or the arguments list for the get out in brackets, it'll insert a blank dimension, like a singleton dimension there. So this will give us a row vector. And if we instead put colon, comma, none, it'll give us a column vector. Does that make sense? So by using none, you can just kind of insert a singleton dimension somewhere in your array. And I do that up here only because models actually expect you to give them batches. And this makes us a batch of 1 here. That's all that is. So we run this model to find the actual label. Now keep in mind, what the model gives us is a vector of 10 values. So if we want to figure out which of the values it's actually predicting, we need to take the maximum, we need to take the index of the maximum value, which is calculated by the argmax function. Everyone heard of argmax? So argmax is basically NumPy has an argmax too. If you ask for the argmax, it tells you the index of the highest value. So these are all going to be 2 because the highest value is 3 and its index is 2. That's what argmax does. So again, if the first value in the model's prediction is the highest value, that means it's predicting a 0. If the next value is the highest value, it's predicting a 1, etc. So we say label equals torch.argmax of pred. And then we can just convert that into a string. We're going to do this for both the y and the label. So get the string of whatever y is, and the label name is the string of whatever label is. And then I'm just going to set the axis title to be estimate label name. So this is what the model's estimating. And then true value is the y name. And I'm going to turn the axis off, and that'll be it. And then once we've plotted one of those, it'll just break. Okay. Okay. So here's a set of predictions. And what you can probably see is that it's doing okay. We didn't train it very long. And this is actually a relatively difficult problem. And we gave it a very simple neural network. Here it's actually got 3 of them, right? This it thinks is a 0. And in general, something you might notice is that it often, if it's confused, it'll guess 0. And there's reasons for that. I'm just going to run this a few more times. We'll get different answers. So here, again, it seems to get the 0 right. These it thinks are 0, which is very wrong. So this one it didn't do very well in. Gets the 1 right here, gets the 2 right here. So you can see that it's getting them right about half the time. Now, random chance, of course, would be 1 in 10. So it's doing a lot better than random chance. But as you can tell, this simple neural network wasn't quite able to do a very good job at this problem. Now, my suspicion is this same neural network would actually be fine if we trained it for like an hour and we gave it a bunch of examples over and over again. We just don't really have time to do that today. But this is basically the whole kind of pipeline for how you can build and train a model in PyTorch. And while I realized that a lot of this went very fast and we went over a lot of kind of complicated concepts, this is sort of the basic workflow that I use for building convolutional neural networks and all kinds of things. So I'm happy to take any questions. We do have a little bit of time, so after questions, I can talk a little bit about convolutional neural networks or whatever else people are interested in. But yeah, any questions before I do that? Yeah. Yeah. That's a great question. So I'll say real quick that this tutorial is actually based on a PyTorch tutorial that's out there. The original, I believe, uses a fashion data set of little images of clothing. It's like little images of like boots and jackets and stuff. And in past years, if like you go to the same lecture from like last year, you'll recognize it as being very similar, but using that data set. So I started learning from those kinds of examples on the PyTorch website. They aren't always the easiest to go through, but a lot of them are very good. A lot of the tutorials on pytorch.org are quite good. And I think we just go to pytorch.org/tutorials. There's a whole bunch of them. And what I would recommend if you're trying to get started with your own like convolutional neural network or something is to find a tutorial that's pretty close to what you want to do and to take the code from that and to start editing it and working with it and seeing if you can get it to work with your problem. As a general rule, if what you want to do is work with images and have them predict labels, kind of like we did here, that's something that there's a lot of machinery out there for and a lot of libraries and things, and you can probably do that pretty easily and not worry too much. If you want to do something more complicated, like there's what's called geometric deep learning, where people will like take the graph of the surface of the brain and use that as if it were an image, kind of. That kind of stuff gets much more complicated very quickly, and there just aren't very good libraries out there for it. So as long as you're working, my recommendation would be early on, try to make everything an image if you can, and you often can turn problems into images. There's lots of tooling for that and lots of good examples online. Yeah. And I do often code with my old code open as a reference. That actually is very, very accurate. Yeah. Any other questions? Okay. Well, we have about 15 minutes left, it looks like. So I didn't really prepare anything on convolutional neural networks exactly, but I can talk just briefly about them if people are interested. That's generally people want to hear about them in my experience. So convolutional neural networks are fundamentally just neural networks like the ones we built. They're just organized in a particular way that is both computationally efficient and resembles the human visual system or the mammalian visual system in general. So the way I typically think about the human visual system is that information enters your eyes and hits your retina, and that's on your retina is where the first neural signals get generated, and there's basically a layer of filters going up through your retina and your lateral geniculate nucleus and your V1, V2, V3 visual areas, and they all do something to the data and then pass it on to the next layer. Now, this is a very, very simple model of the visual system. This isn't perfectly accurate, but this is at a first approximation. This is pretty accurate. And the system we just built, the neural network we just built, you notice, was literally a sequence of filters applied to the data that came in as input. So the data came in as input. It went through this linear filter, this rectified linear unit, this other linear, et cetera. That was just a sequence of filters. Now, these filters were not organized in any way like visual filters. They were just random filters with random weights. But in the visual system, early on, there's a set of filters that are designed specifically to get like edges between contrasts out of your visual field, where you've got what's called a Gabor patch. Let me see if I can just find a quick image. Yeah. So this is a Gabor patch. It's kind of a sinusoid modified by a Gaussian. And you can imagine, let's see if they have another example. Let me just find, I can find a better example here. These are all high frequency Gabor patches. What I'm looking for is a low frequency Gabor, like these. So this is like a very, oh, well, okay, those are moving. Here we go. Okay. This is a pretty simple, this one, these are small Gabor patches. There's basically like high values and low values in those Gabor patches. And if you have a bit of your vision where you've got like a line, like where it's dark over here and it's bright over here, and that falls along this Gabor patch, it kind of lines the high parts of the Gabor patch up and the low parts up with the brightness and the darkness in the image. And that drives a really strong response from that neuron. The idea is that if you've got if your retina is kind of full of these Gabor patches, and so at every position on your retina, there's some cells that are calculating how much contrast there is between this side and this side. Oops. And they fire stronger when they get high contrast. If you have dark stuff over here and light stuff over here, that is going to drive pretty much no response in that Gabor patch because the line isn't lining up with the Gabor patch. I don't know if that makes sense to anyone who doesn't study vision, but the basic idea is that there's these little filters in your eye and in your brain where information kind of goes through these filters, and the encoding of what's represented gets more complex as you kind of go through that hierarchy. Convolutional neural networks, what's kind of innovative about convolutional neural networks is that they can apply that same kind of operation at all points in an image very efficiently. So in a convolutional neural network, not sure if I have something I can draw here, I can try. So you've got like an input image, and you've got a kernel. And our kernel might be something like a Gabor patch, where we've got high values here and low values here. I don't know if that schematic works really, but the idea is we line this image up so that it's right here on the image, and we calculate the product of these values, these high and low values, with whatever's in the image. And that gives us a single value that says, how much does this part of the image look like this filter? And then we slide the filter over, just 1 pixel actually. So we really have like an overlapping one here. And we do the same thing. We say, how much does this filter overlap with this part of the image? And that gives us our next value, which is going to be right next to it. And we're going to do that. We're going to just slide this filter over the image and down the image and across. We're going to line it up with every point on the image. And what we produce at the end of that is another image the same size as this original image, but it's an image where every pixel is telling us how well the original image, or how much the original image looks like this Gabor filter. So far, so good. Any questions on that so far? So that process is called convolution. It's where we're kind of sliding 2 things past each other and seeing how well they overlap at every position. And that's a very powerful operation. If you've got something like this filter and you run it over the whole image, parts of the image where there's like a line are going to produce a really clear line in the output image. And it doesn't have to be just a line, like where there's like a difference in contrast, I should say. We'll produce a clear image in the output image. So there's a lot of powerful kind of computations that can be done using just a very simple kernel and convolving that with an input image. And a convolutional neural network is just a series of these kernels that you run across progressively calculated images. So in a convolutional neural network, we might start with a Gabor filter like this, and we produce an image that is Gabor filtered, and then we'd have a more complicated filter that would be something else. And we would just keep running these layers of filters. So really, they're the same kind of thing. There's not really a fundamental, like there's not a theoretical difference between a convolutional and a regular neural network. Convolutional neural networks just use this convolution operator. Like I said, the convolution operator can be calculated very efficiently. This has to do with the math of the Fourier transform. You can perform a Fourier transform and do a vector product in Fourier space and then unFourier it, and then you end up with a very efficient calculation for the convolution. And so I think a big part of the reason convolutional neural networks have taken off are not only are they good at the same kind of things our visual system is because they were designed very similarly to it, but they can also be run very efficiently. You can get a lot of very complex data out of them very efficiently because of this efficient convolution operation. If that whole thing about the convolution operation being efficient sounded really cool and you want to know more about that, I'm happy to nerd out about it, but we're not right now. That's we don't have time. Okay, so I don't think we have time. Whoops, I didn't mean to do that. Sorry. I don't think we have time to actually build a neural network, convolutional neural network, but I will just show you really quick kind of what one would look like. Basically, instead of having this linear, we would just use like torch.neuralnetwork.convolution2D. And we would tell it how many layers were in our input image. That's like how many channels. So like if you were giving it a red, green, blue image, like a traditional RGB image, that's a 3-channel image, one for red, green, and blue. If you gave it a grayscale image, that's a 1-channel image. You can have any number of, you don't have to have just 1 or 3 channels. You could have any number of channels in your image. But for a convolutional neural network, we typically say, okay, there's 1 channel in the input and we want 1 channel in the output. And we want our kernel to be like 3 pixels by 3 pixels. And that's the input, that's the layer we would give it. And PyTorch basically figures out the rest. So PyTorch is quite good at this kind of convolutional, like there's a lot of PyTorch code under the hood that does the convolution stuff that works really well. Last night, just to test some stuff, I built a really quick convolutional neural network where I just replaced these with conv2ds. And then I had to add 1 linear unit at the end that turned it into a 10 feature output. But other than that, it worked just fine. It worked just as well as the neural network we had built. If you're interested in that, I can send you code for it later. I don't have it handy. Yeah, Mohammed, go ahead.
Could you please, if you have time, could you please talk a little bit about graphical neural networks?
Graphical neural networks.
Mhm.
I'm not sure what that means.
So I think based on my little knowledge, these are neural networks that could deal with functional MRI connectivity things, like takes into
Oh, okay.
functional connectome,
Yeah,
like or connectome matrix or something like this.
yeah. So I think typically these are called just graph. Uh, well, I guess I'm not sure. I think they're typically just
Yeah,
called graph neural
graph
networks.
network
Yeah.
or graph. Yeah.
Yes. So the idea behind, okay, and I think specifically you mean convolutional graph neural networks, is my guess.
Yes,
So
correct.
yeah, so okay, so I talked about this convolution operator as something where you slide it over this, you slide a kernel over an image. In theory, there's no reason that that kernel has to be an image. It could instead be a graph. So you could have a very large graph, and then you could have a very small, like kernel graph that consists of just like 5 connected nodes or something. And you can, in theory, at least slide that kernel around the graph depending on how your graph is shaped. This isn't something I'm an expert on by any means. But like if, for example, the Ribeiro et al. Paper that came out a few years ago, where they predicted retinotopic maps based on a graph neural network, that's what they used. Was it's essentially the same operator. It's just that they've abstracted the math from working on images to also work on graphs. That's about as much as I know about them, though, to be honest. I can't tell you a whole lot more.
Okay, thank you.
They're useful because you can run them on both like graphs like you were saying, like resting state or connectivity graphs, but also on like the triangle mesh graphs that make up the cortical surface in 3D models of the brain. That's where you find those a lot. Yeah. Yeah.
Is there like even in PyTorch, is there like a set of classic networks that you can just okay,
Yes.
let me find this one, let me find this one, instead of constructing new layers. This type of neural network has worked on that kind of example. Can I start with that?
Yeah, that's a great question. So for those of you on Zoom, the question was in PyTorch, are there built-in or like a kind of classical neural networks available to be used inside of other neural networks? And the answer is yes. And in fact, one of the, like, for example, one of the very commonly used networks for image classification, like this problem we're doing here, is called a ResNet. And I don't remember offhand, it might be as simple as torch.neuralnetwork.resnet. Maybe not. Well, I don't remember it offhand, but I am quite sure that if I just Google it, we'll find it. Yeah, so there is, I see they've changed this recently a little bit. So they now have a PyTorch hub, I guess, where you can upload the weights to your models. And so they're like, if you are familiar with AlexNet or ResNet or all the various different kinds of ResNets, UNets, these kinds of, they've got pre-trained networks up there that you can use. And because they're all written as PyTorch models, you can literally just stick them as a layer into your own model. And you can say, okay, the first step in this neural network is to run a ResNet, and then we're going to go on from there. And that's a very common way to build these. Yeah. Yeah. Mhm.
One of the concerns I have is overfitting
Mhm.
because you're constantly propagating. Do you feel like that propagating neural network is worth it? Would it take a lot of time to build, and you
Oh,
really
boy.
have confidence in your math, and then you're gonna end up something you go over it at the end?
So that's a great question. I honestly, the backpropagating neural networks are pretty cutting edge at this point. I know almost nothing about how they work internally. So I unfortunately can't answer that question for you at all. Sorry. I would, if you want to do like a birds of a feather session on that next week or something, I'd be really interested in learning more about it, but it's just something I can't tell you about right now. Sorry. Yeah. Yeah, so there's a kind of interesting principle here, which is that whatever problem you're solving with the CNN, if you can make that problem easier for the CNN before it starts, then you can probably reduce your training time a bunch and make it use a smaller network. And one of the things about spectrograms is they take a lot of information implicit in the signal and they make it very explicit in the image. And so you basically are saying, look, in the sound file or whatever you're trying to classify, the data's there, but it's really hard to get at. That CNN's got to figure out how to do a Fourier transform and then do a short-term Fourier transform and then to make that into an image or something. And if you can do that for it, because that's an easy thing for you to do, you'll have a much faster to train network, basically. So that's where the kind of thing I see a lot. You can absolutely use 1D sound data on a CNN. CNNs can be 1D. But yeah, I think that's the reason people would do that typically, is that it makes the problem easier. Yeah. Exactly. Yeah. Yeah. Okay. I think we're a little out of time. Thanks everyone for coming and for the good questions and everything. I'm happy to talk about this more later or next week. Again, if there's like if you want to ask about it in the review session, or if people want to hear about it in a breakout, just let me know. But yeah, thanks everyone. All right, we'll be back here at 3:30 in the other auditorium, I believe. So I'll see you all then. Oh, Ashley, did you have a question?
I do, if possible. I know we're kind of out of
Yeah.
time. Sorry, it actually might be a really stupid question. I'm just trying to figure this out. We went over this example with like a regular image. What kind of modifications would you need to do to apply this to neuroimaging data? Can PyTorch handle like a 3D image, or do you just kind of like flatten the array in a certain way, or like how would you do that for MRI?
Yeah, so I've actually written a 3D CNN for trying to segment visual areas out of a 3D image, like a T1 weighted image. And it absolutely does work, but the standard libraries are all for 2D CNNs. And so you have to go find, there's other people who have written 3D convolution algorithms out there. You just need to go get one and use it. So it's absolutely possible. What I will say is that I found that if you're trying to do training on like structure data, in general, it's a little easier for the CNN to do things if you make a 2D image out of a projection of the cortical surface, if that makes sense for your problem. It's just that the surface data is a little bit easier for the CNN to understand, whereas the T1 weighted data, like the brain is folded and complicated, and it's got to figure out like that kind of, it's got to find some way to represent that in the 3D CNN. So what I found is just that 2D CNNs are a little easier to work with, but there's nothing fundamentally like theoretically limiting about a 3D input. Yeah.
Cool, awesome. That's really helpful. Thank you.
Yeah, no problem. All right, we'll see
Bye.
you.